Before the Webb set out into space to reveal the most remote and ancient secrets of the cosmos, it was said, "I think the greatest promise of the James Webb Telescope is that it will provide answers to questions that no one has thought of yet." And indeed, the Deputy Technical Project Manager at NASA's Goddard Space Flight Center was proven right by this prognosis. Today, we are wondering how it's even possible for the Webb to detect structures in space that seem simply impossible according to our established models. But how do you deal with discoveries that are so inexplicable that they even stand in stark contradiction to current cosmology? In the context of this astronomical dilemma, there is currently much talk that the James Webb Telescope has practically overturned everything we thought we knew about the cosmos and the Big Bang. But has our understanding of the universe really been destroyed? Well, the bottom line is that the truth is somewhat more nuanced, but that also makes it much more exciting. To get a sense of the extraordinary capabilities of the James Webb Telescope, it's worth looking at the following example. In theory, the $10 billion device could detect the heat of a bumblebee on the surface of the Moon from Earth. In practice, however, Webb did not find any fluffy insects in the depths of the cosmos. Instead, it found a whole series of mysterious objects that simply do not match our tried and tested cosmological models. First and foremost, of course, are the sensational universe breakers. After Webb's near-infrared camera, NARCam, examined a section of the sky near the Big Dipper, experts identified 6 reddish points of light in the images that turned out to be real mysteries. Based on the redshift, scientists determined that the emitted light had taken more than 13 billion years to reach our earthly eye. We are therefore dealing with structures that existed 500 to 700 million years after the Big Bang. Furthermore, the characteristics of the light points suggest that these are very early galaxies, and indeed, galaxies that shouldn't actually exist in this form. Astronomers had expected to find only tiny baby galaxies for this early chapter of the universe. After all, our theory suggests that at that time, there was simply not enough normal matter to pave the way for galaxies the size of our Milky Way today. The experts were therefore all the more perplexed when they were confronted with precisely that. All 6 early galaxies actually already contain more than 10 billion solar masses of stars, and one of them could even have a stellar mass of over 100 billion solar masses. Now, there are basically 2 ways to explain the existence of such early galactic heavyweights. Either the matter density in the young cosmos was 2 to 5 times greater than previously thought, or the galaxies formed in a way that is completely alien to us. In this context, the confusing discovery was unsurprisingly described by experts as a real problem for science. Due to their inexplicable dimensions, the structures quickly earned the unglorious nickname universe breakers. However, they ultimately only laid the foundation for a series of further confusing finds that raised serious doubts about our understanding of cosmic development. Because a few months ago, Webb did it again, with another early galaxy added to the star map that existed just 290 million years after the Big Bang, and once again turned out to be an astronomical mystery. Although the galaxy already existed at a time when, according to current theory, the first stars were only just being formed, it's already incomparably luminous. The researchers' analyses showed that the structure already contains several hundred million solar masses of stars. But how could such a massive galaxy form in less than 300 million years. In fact, scientists assume that the star cluster took about 100 million years to grow to its observed dimensions, and the spectroscopic studies indicate that several very massive stellar generations have passed through their life cycle before the galaxy came to the attention of astronomers. But what do these mysterious discoveries mean for the big picture? After all, if we were already mistaken about the structure formation processes in the universe, could it not be that we are also wrong about much more fundamental assumptions, such as the birth of the cosmos? Well, who knows? But amazingly, the greatest astronomical crisis of our time now seems to be experiencing a promising turnaround, at least in part. In fact, the latest research suggests that the ominous red light does not actually come from inexplicably star-rich galaxies, but instead comes from active black holes, which are enthroned in the centers of the galactic premature babies. In detail, the mass monsters, with their extreme gravitational force, attract matter. The matter accumulates in so-called accretion disks. These disks, in turn, consist of hot gas and dust and rotate at a crazy speed of up to 1,000 kilometers per second around the black hole. A study co-author stated that this finally solves the serious problem that has so challenged our understanding of the universe. NASA also commented on the new findings and emphasized that, contrary to all the headlines, cosmology has not collapsed. But does that really mean that our standard model is off the hook for good? Well, not quite yet. Because the bottom line of the evaluations of the Webb sample surveys, which span several 100 million years, is that around 70% of the red dots show signs of gas movements that are typical of black holes. But the remaining 30% is, of course, a completely different matter. Furthermore, the black holes themselves are still surrounded by big question marks. After all, it seems that they initially appeared in large numbers about 600 million years after the Big Bang. But then, mysteriously, they suddenly decreased again 900 million years later. One explanation for this is based on the assumption that as star formation spread, the amount of dust and gas also decreased, and that this caused the light emitted to gradually shift from red to blue, and thus into a range that the James Webb Telescope cannot detect. But while this theory sounds plausible, it has yet to be confirmed in future investigations. That said, we should not forget that the alleged universe breakers are by no means the only mystery that Webb has already added to the star charts. While black holes in this case still held the key to solving the problem, they are causing astronomers all the more headaches elsewhere, such as the inexplicably massive black hole, which weighed in at over 1 billion solar masses when the universe was still in its infancy, just 770 million years after the Big Bang. Is the Big Bang theory wrong? But was the universe really still in its infancy back then? Or could it be that it actually looks back on a completely different past than the Big Bang theory suggests? Basically, the Big Bang theory assumes that the universe unfolded from a tiny starting point about 13.8 billion years ago, or to be more precise, space-time and matter emerged from an original singularity. But although the Big Bang theory has long held a prominent and established position, there are more and more researchers these days who are turning their backs on this long-standing idea. Among them is a British physicist and Nobel Prize winner who does not see the Big Bang as the literal beginning of everything, but merely as the explosive transition between two cosmic chapters. In fact, this physicist is convinced that the universe has always been subject to a fixed cycle of destruction and rebirth. In detail, the cosmos would always expand until all matter has disintegrated and become light. This extreme environment, in which nothing has a time or space reference to one another, would inevitably lead to a new Big Bang over and over again. There is no question that this idea sounds extremely exciting on paper, but here's the kicker. This physicist actually claims to have found tangible evidence for this exciting model. More specifically, he's referring to some striking circular spots in the cosmic microwave background that were detected in satellite data. And just to clarify, the cosmic microwave background radiation, or CMB for short, is a relic from the early days of the universe, created around 380,000 years after the Big Bang during the so-called recombination epoch, and it fills the entire universe to this day. This physicist believes he has detected a series of telltale Hawking points in it, and thus relics that come directly from a precursor universe. Because when black holes evaporate completely into Hawking radiation at the end of a cosmic chapter, they would take all of the radiated energy with them into the subsequent universe in the form of a single Hawking point. In view of this exciting discovery and all the cosmological inconsistencies uncovered by the James Webb Telescope, is it possible that our world does not correspond to the one universe at all, but only to the current cycle? Well, that is precisely the question, because the rest of the research community is not exactly unanimous in its approval of these statements. But whether it's the Big Bang, a cyclic universe, or something completely different, the bottom line is that some fundamental questions remain unanswered either way. After all, what led to the universe coming into being out of nothing 13.8 billion years ago, or at some point earlier? Was there a trigger, or was it mere coincidence? And what was before that? These are all questions to which experts do not yet have any clear answers. But who knows? Maybe the next hot lead is just around the corner, waiting to be discovered by another exciting Webb find. And now, we'd like to point you in the direction of the subscription button. Simply click the thumbs up and subscribe to never miss a new video from us again. We'll see you soon. The James Webb Space Telescope continues to challenge our cosmic understanding with each new observation. Recent data reveals galaxies so ancient and massive that they defy conventional models of cosmic evolution, structures that appear fully formed, when, according to our theories, they should only exist as faint protogalactic clouds. These cosmic anomalies suggest either flaws in our understanding of dark matter distribution or entirely unknown physical processes operating in the early universe. One particularly baffling discovery involves a galaxy observed just 300 million years after the Big Bang, already containing multiple generations of stars. This implies star formation began far earlier than predicted, possibly within the universe's first 100 million years. The implications are staggering. Either the conditions after the Big Bang were radically different than we thought, or our entire timeline of cosmic dawn needs revision. Equally puzzling are the supermassive black holes found in these primordial galaxies. Current models struggle to explain how black holes grew to billions of solar masses so quickly. Some theorists propose direct collapse scenarios where massive gas clouds bypassed star formation entirely, collapsing directly into black holes. Others suggest primordial black holes formed in the instant after the Big Bang, seeding the early universe with gravitational anchors around which galaxies could form. The telescope's infrared eyes have also detected unexplained structures, vast arcs and rings of galaxies spanning distances that should be impossible in a 13.8 billion-year-old universe. These cosmic megastructures, some stretching over 3 billion light-years, challenge the cosmological principle that matter should be evenly distributed on large scales. New spectroscopic data reveals another mystery. Certain early galaxies show chemical abundances matching stars billions of years more mature. This suggests either incredibly rapid metal enrichment processes or that pockets of the early universe evolved under different physical laws. Some researchers speculate about localized variations in fundamental constants, while others propose exotic dark matter interactions. The cosmic microwave background, our snapshot of the infant universe, shows subtle anomalies that align with some of Webb's findings. Certain large-scale patterns appear statistically unlikely under standard cosmology, hinting at pre-Big Bang physics or a more complex inflationary period. As Webb peers deeper, it's revealing a universe far stranger than we imagined, one where galaxies form too fast, black holes grow too large, and structures assemble too soon. Each discovery opens new questions about dark matter's nature, inflation's duration, and even the fundamental validity of general relativity on cosmic scales. The coming years promise even more revelations as Webb continues its mission, potentially uncovering evidence of cosmic strings, primordial gravitational waves, or other relics from the universe's first moments. One thing is certain. Our cosmic origin story is being rewritten in real time, with each new observation challenging long-held assumptions about how the universe came to be. These discoveries don't just fill textbooks, they force us to reconsider the very nature of time, space, and existence. The more we learn, the clearer it becomes that the universe's greatest mysteries may still lie ahead, waiting to be revealed in the faint infrared glow of our cosmic dawn. The latest Webb observations have uncovered something even more perplexing: galaxies that appear to be too blue for their age. These cosmic anomalies show star-forming activity at rates that should have exhausted their gas supplies billions of years ago, yet they shine brightly in the early universe. This suggests either unknown mechanisms replenishing interstellar gas or flaws in our understanding of stellar evolution under primordial conditions. Even more startling are the recent detections of what astronomers are calling dark galaxies, massive structures rich in dark matter but nearly devoid of visible stars. These ghostly formations, detected through gravitational lensing effects, challenge our models of how normal and dark matter interact during galaxy formation. Some theories propose these could be failed galaxies, where star formation was somehow suppressed, while others suggest they represent an entirely new class of cosmic object. Webb's mid-infrared instrument has revealed another cosmic puzzle: enormous dust clouds in galaxies that existed when the universe was just 5% of its current age. This dust appears too abundant and too mature, requiring supernova rates that would have disrupted these fragile early galaxies. The discovery implies either faster dust formation processes or that the first stars produced dust more efficiently than their modern counterparts. Perhaps most revolutionary is Webb's detection of large-scale structures that appear to violate the speed of light's cosmic limit. While these aren't true violations, but rather artifacts of space-time expansion, their sheer scale forces us to reconsider the fine details of inflationary theory. Some cosmologists are now exploring models where inflation occurred in multiple phases, or at varying rates across different regions of the early universe. The telescope's spectroscopic capabilities have also identified peculiar chemical signatures, galaxies with unexpectedly high nitrogen abundances at redshifts previously thought impossible. This unexpected nucleosynthesis pattern suggests either unknown stellar processes in the early universe or that some portions of space underwent radically different chemical evolution. Recent analysis of quasar light from the epoch of Ryanization shows puzzling absorption features that don't match any known atomic transitions. These spectral anomalies could indicate exotic states of matter, previously unknown quantum effects in early plasma, or even, more speculatively, signatures of dark matter interactions. As Webb continues its mission, every new dataset seems to reveal more questions than answers. The emerging picture suggests our universe's infancy was far more complex and dynamic than standard models predict. A cosmic Wild West, where known physics operated differently, where matter organized itself in ways we're only beginning to comprehend. What makes these discoveries particularly thrilling is their potential interconnectedness. The overmassive galaxies, the premature black holes, the anomalous chemistry, they may all be facets of a single deeper cosmic truth we haven't yet grasped. With each observation, Webb isn't just adding pieces to the puzzle. It's revealing that we may have been working with the wrong picture all along. The coming decade of Webb observations promises to either resolve these mysteries or, more likely, uncover even deeper ones. As we stand at this crossroads of cosmic understanding, one thing becomes increasingly clear. The universe is far stranger, far more wonderful than we ever dared imagine. And the greatest revelations may still be waiting in the darkness between the stars, ready to challenge everything we think we know about reality itself. The James Webb Space Telescope's unprecedented resolution has now detected what appear to be fully formed globular clusters in galaxies less than 500 million years after the Big Bang. These dense collections of ancient stars shouldn't exist at such early cosmic times, as current models require billions of years for their formation. Their presence suggests either that star cluster formation operated under radically different physics in the early universe, or that our understanding of stellar aging processes is fundamentally incomplete. Equally baffling are the recent observations of rogue planets, not orbiting any star, already existing in substantial numbers during the universe's first billion years. These free-floating worlds, detected through microlensing events in early galaxies, raise profound questions about planet formation mechanisms. How could such planets form so quickly without the benefit of mature protoplanetary disks around stable stars? Some theorists are now considering exotic scenarios involving direct collapse from primordial gas clouds or even remnants from a previous cosmic cycle. Webb's spectroscopic analysis has uncovered another profound mystery. Certain early galaxies show oxygen-to-hydrogen ratios that match modern stellar populations, despite existing when the universe was less than 3% of its current age. This implies an incredibly rapid and efficient period of early metal enrichment that current supernova models cannot explain. The data suggests either that the first stars produced metals far more efficiently than predicted, or that unknown nucleosynthesis pathways existed in the early universe. Perhaps most startling is Webb's detection of what appear to be fully formed galactic disks at redshifts previously thought impossible. These mature, rotating structures exist at cosmic times, when current models predict only irregular, chaotic protogalaxies. Their existence challenges our fundamental understanding of angular momentum distribution in the early universe and suggests that large-scale structure formation may have occurred much faster than currently believed. The telescope has also revealed peculiar patterns in the cosmic infrared background, subtle but statistically significant anomalies that correlate with neither known galaxies nor the cosmic microwave background. Some researchers speculate these could be signatures of decaying dark matter particles or even topological defects in space-time left over from the universe's earliest moments. New analysis of quasar absorption lines has identified what appear to be coherent structures spanning hundreds of thousands of light-years at redshifts greater than 7. These cosmic filaments show metal enrichment patterns suggesting they formed through processes unlike anything observed in later cosmic epochs, potentially pointing to fundamentally different intergalactic medium conditions in the early universe. As Webb continues its observations, each new data set reveals a cosmos that appears increasingly foreign to our established theories. The emerging picture suggests that the laws of physics themselves may have operated differently during the universe's first billion years, or that we're seeing evidence of phenomena that current models don't account for. From inexplicably mature structures to anomalous chemical abundances, the early universe, as revealed by Webb, appears to have followed a different set of rules we're only beginning to decipher. Thank you for joining us on this journey through the wonders of space. Your support makes it possible to continue sharing the marvels of the universe with the world. We can keep exploring the stars and uncovering the secrets of the cosmos. Don't forget to check out our playlist for more incredible space content. Until next time, keep looking up